Welcome to Real Physics and to another talk at the wonderful conference organized by Shiloh and Anastasia from the Demystify Sci podcast. And I'm talking why a variable speed of light cosmology is so much smarter than both the conventional Big Bang picture and the steady-state infinite universe models. Look, if geniuses like Ernst Mach, Albert Einstein, Erwin Schrödinger, Paul Dirac, Dennis Sciama and Robert Dicke have worked in that same direction. You just should pay attention to it.
Today we are going to pick up where we left off last night at the panel, which is redshifts, distant galaxies. Maybe we'll unpack these supernova curves a little bit more. I still have questions about that. But to kick things off, we have Dr. Alexander Einstein back again by popular demand. So he's going to talk to us about variable speed of light cosmology. Here you go.
Yeah, thank you very much again. Welcome to the talk. My title is Variable Speed of Light Cosmology, a Search for Answers. And I did change my talk yesterday. I added some slides because that's what I'm observing at the conference. You know, I mean, all these very convincing contradictions and the Tolman test, take this, and the large cell structure doesn't add up with the Big Bang model. And on the other hand, people towards the mainstream, more leaning towards the mainstream, saying, well, steady state, come on, okay, infinite universe, give me a break. So I see this fight, and well, this morning I'm very, very agreeable, I should say, and I can assure you, you're both right in claiming that the other one is wrong. So, and no, but seriously, what if there is a third, smarter possibility for resolving these issues? And spoiler alert, it's based on Einstein. Based on Einstein's first idea about general relativity. So I'm going to explain this in detail, but I mean, technically, you could also call this tired light, but I really don't like it because it begs the question, what are you tired of? Sorry, but I mean, you have to provide an explanation, a mechanism. I don't feel satisfied when I hear, oh, it could be anything. No, I mean, we have 700,000 galaxies with Redshift on my computer, the data. You need a damn good explanation for this. And not just some fitting or some explanation. What I will give you today is a first principles justification why we need that. It comes up as something necessary if you follow up these ideas of Einstein. So, second thing I added, well, all this might seem a little bit theoretical, bold ideas, but you know, we have two problems in physics. One is this crazy string guys and people like that, or inflation, doing theory without contact to experiment. This is one thing. But there is also the second danger, people too narrow at the data, just looking what is topical and seeing what's the last sensation, and then coming up with parameter fitting and missing the big picture. So I'm aware of the danger. Eric in his book says that's kind of the disdain of the master for the slave's work. It's not. I will come back to the experiments and to the evidence, but you know, the whole thing I think has to make sense, and that makes a lot of sense. I will put this at the beginning. I really want explanatory power in physics. I want to have explanations. I don't like free parameters, or even if they're called constants of nature. So there are some bold goals of variable speed of light cosmology. What we try to achieve here is a unification of inertia and gravity, because it's not done yet. As I have already said, the origin of the gravitational constant. I don't believe in gods of modernity. 6.67. No, I have to calculate this. An explanation, as I said, of the cosmological redshift, not just an interpretation. Predicting Dirac's large numbers, I already have outlined. I think these are very relevant. And of course, we want to be in agreement with the confirmed effects of general relativity, and also possibly have ideas, I'm not claiming too much here, but ideas towards solving these serious problems. And, well, ideally even have an outlook for a microscopic theory of matter. So let's start a little bit with the history. Einstein in 1907 came up with the equivalence principle. Inertia and gravitational mass is the same. And I think it's wonderful that he built on that. Yet you should not forget there is not a true explanation from first principles why we have this equivalence principle. The same year, when he started about reflecting upon general relativity, he mentioned variable speed of light in this unknown publication about the principle of relativity and the conclusions drawn therefrom. And there you find the first mention of influence of the gravitational field on clocks, the first mention of a changing variable speed of light. Now he elaborated this in 1911 about the influence of gravity on the speed of light in this publication, and that's the one I quoted before. By means of Huygens principle, he said, okay, we observe from the principle of equivalence that light rays need to be curved, and the most natural explanation is they are curved as, in Huygens principle, as normal waves. They encounter a medium which is more dense, and masses increase these density, and the speed of light has to decrease. So there is a lot of mentionings of Einstein dealing with the, sorry, I'm going too fast here. Yeah, this is 1911, this is 1912. I am going too fast here because Anastasia told me to hurry up, so I... don't spoil the entire... I'm not supposed to spoil my jokes here. There is another reason, and I'll tell you, but I hurry up a little bit here. 1912 he mentions, because some people are not knowing about Einstein and variable speed of light. I mean, he's the founder of the idea. How crazy is that? I mean, everybody knows Einstein, everybody takes him as a crown witness for every fancy phenomenon in cosmology, and you don't know about that basic fact. It's so, just 1912, okay? I don't read it, or you can read it with calm. 1912, another paper. The constancy of the speed of light can be valid only for regions of constant gravitational potential. That means it's not constant, okay? 1912, another paper. The most simple equation of the speed, varying speed of light. 1913, is there a gravitational field? Variable speed of light. Einstein's 1913 draft theory, together with Grossman, depends on the gravitational potential. Special variability of the speed of light, 1913. So, yeah, talk given in Switzerland, 1913. And now, I mean, the real reason why I'm going so fast, I used to imagine this one. It is really, I imagine that each of this slide being a slap in the face of these crazy Wikipedia editors, because a couple of years ago it was mentioned, oh, Einstein, the founder of variable speed of light, and then a couple of guys came along saying that, well, we don't know about that, we don't know German, so let's cancel that out. It's not Wikipedia anymore. How crazy is that? Anyway, that's a sideline. Let's go on. 1915, everyone knows this is the year of the development of the final form then of general relativity, And then variable speed of light stops here, right? He gave up. Just that he kept saying that. It's variable speed of light, you know? This is 1916, speed of light in Mach cannot claim unlimited validity. 1916-17, another essay, velocity of take place when the speed of light varies with position. 1918, about gravitational waves, velocity of light depends upon the location. 1920, manuscript for nature. Okay, constancy of the speed of light can no longer hold. 1921, Princeton lecture. Speed of light means it's deflected. So these other slides were, I imagine, slapping the faces of these historians who are just ignorant about or keep claiming that variable speed of light has been given up. It's not true. And fortunately, there are people pushing against this wrong narrative, like Gareth, where are you? Congrats for your channel, for your great video. He also puts all the quotes. And, well, there is, I'm missing a slide here. It comes later anyway. Yeah. There are a couple of criminals who are responsible for that. One of them you mentioned is Peter Bergman, and the other one is Abraham Pais, which they just didn't like the variable speed of light, and they erased it from the biography. I mean, that's not what a biographer is supposed to do, I think. Well, coming to content here, why did Einstein give up on variable speed of light? I mean, how he didn't give up, but why he switched. So in his 1911 paper, he developed a theory of variable speed of light. And what you have to keep in mind here, that always C equals the frequency times the wavelength, okay? That once you change C, that change has to go into the wavelength or the frequency also. And the mistake Einstein made in 1911 is considering only variable time scales. He didn't think about variable length scales. And this took 50 years to be corrected. Unfortunately, Robert Dicke did it in 1957. And so Einstein switched over with his draft theory, and he was influenced by Grossman and fascinated from this differential geometry. And it's just beautiful math, you know. He was very fascinated, so he developed this, and there was a wrong version of that geometry, and then he corrected the wrong version, but being always in the geometrical, already in the geometric picture here. So eventually he realized that he had to take into account also the wavelength, or if you want, the geometric approach pushed him towards that insight. So he came up with the correct solution in 1915 with a light deflection of 1.75 arc seconds instead of 0.84. But the thing is, you could correct variable speed of light as well, no problem, without switching to that geometrical interpretation of general relativity. So it's kind of, well, Einstein probably himself believed that there was something with the other approach, and he believed that he needed to do this in that geometric way, but it's not necessary, okay? That's an important take-home message. Yeah, that should have been, I think I just mixed up that. Another slap in the face, let's say, okay. And this is Abraham Pais, I already mentioned, yeah. What did I do? I searched in his biography for variable speed of light, and there was one point, and he was very dismissive about that, but I mean, you cannot bring just your own opinion about, yeah, anyway. So the important take-home message is here, it's the same thing. Either say general relativity is described in a curved space with constant c, or in a flat space with variable c. It's just that light takes the fastest path. You can also draw a map of Portugal, how to get to Lisbon, and you don't go across the beach or across the woods, you take the highway, and it's a curved way because it's faster than your velocity. So these are equivalent descriptions, and that has been proved by many people. Just a reminder, if you're talking about variable speed of light, you might naively think, oh, this is 300,000 kilometers per second, how this is going to change. No, this is a definition, okay? This is defined by our current unit system. You can debate if this is useful or insightful or not, but just keep in mind that you're not directly observing variable speed of light, but you have to look at the changes of the frequencies and the wavelength, which would change accordingly. A couple of other more or less insignificant quotes, but in a lot of books that if you look up, you can find also this concept of variable speed of light. And but it's largely almost forgotten, so people sometimes had to reinvent it, as in this interesting paper in 1960. I just like to give credit to people who have thought about this, and there is one guy from Belgium who wrote a series of papers proving really seriously the equivalence of the variable speed of light approach to general relativity, reproducing all the known tests. And then also to give historical credit, there is a precursor by Wilson, even in 1921, thinking about that. So, but let's come now to the broader picture here. What we want is, not only an explanation of these effects, but a broader unifying picture. And one important figure here is, of course, Ernst Mach. And Einstein himself was giving a lot of credit to Ernst Mach. And Mach indeed has anticipated the principle of equivalence with his famous Newton bucket experiment, saying that it doesn't make sense that absolute space of Newton inertia presumably comes from the distant universe, and if the distant universe would rotate around us, then the water would rise up the walls as well. So this is Mach's principle. Watch Andreas' videos, or we had a nice talk. He also has these fantastic experiments. He came up with his, what was Brazilian coffee in there? But it works also, what I'm saying is Mach was anticipating the principle of equivalence in the sense that he said, well, if inertia is determined by the distant masses in the universe, so gravitation is. And that also implies that the constant of gravitational constant itself should be a function of mass and mass distribution in the universe. The tragic thing is Mach couldn't, he died in 1916, cosmology didn't exist. He couldn't see the data, he couldn't verify his theory. So we had to be patient. And then in 1953, there is a fantastic paper, and I'm really featuring this guy, Sciama, who published a paper about the formula of the gravitational constant, and that really intrigued me because I had thought in the same direction. I said, oh, it's incredible how this fits, and there must be someone who has done this before. Yes, Sciama, 70 years ago. Now he came up with this formula, and how to get things in order here. I was fascinated by the formula in the first place, but what he did actually, and I didn't read carefully the paper for about 20 years, he also has a fantastic idea how to unify inertia and gravity in what he did is a vector potential. And there is a guy from Britain now, Jonathan Fay, who does a PhD on the work of Sciama, and he reminded me of that, and so I did a little clickbaity video recently where I outlined the achievement of Sciama and also the work of Jonathan Fay, who had publicized it again. So it's really a very interesting thing, and we're not done here, to be honest. There is some serious problem with the theory, and a couple of smart guys are working in that direction, but we can only hope. But if you want to have the big picture, I think we need to do that. We need to try to find a reason a really good reason for the unification of gravity and inertia, and definitely we have to explain the gravitational constant. And giving credit to other people, there is even Erwin Schrödinger in 1925. Look at this, a paper about cosmology, where he speculates the gravitational potential of all the universe. He didn't know about all, couldn't know about all the universe, but he speculated, oh, couldn't this be the speed of light? Yeah? Because if you put g times mass divided by radius, the unit is meters per second squared, meters squared per second squared. So presumably in this, with this idea, he speculated about the variable speed of light. And just to remind you, this is, I mean, if that succeeds, it's huge, because it's that kind of revolution I outlined we need to have in physics. You need that bold idea. Of course, you have to have the proper mathematical theory and formalism, which is missing, I admit. But, I mean, there is a fantastic target inside here, and if you succeed in calculating the gravitational constants from the mass distribution, that would be similar to the Newton's revolution of explaining all these constants of nature, the little g's with a big G, but then in a more general way you would explain the gravitational constant itself. So, where we go next? Robert Dicke in 1957. Let's take a closer look at the guy who discovered or who corrected Einstein's mistake. Well, he didn't know about Einstein. He knew about Mach's principle, was fascinated about Mach's principle, but consider he independently developed the same kind of theory as Einstein in 1911. Of course, now he knew about the tests of general relativity, which Einstein couldn't know in 1911, but he did it in the correct way. He considered that the speed of light, the change of speed of light in a gravitational field, is equally distributed to the change of the wavelength and the frequency, you know? I mean, just to recap, because this is an important point. The presence of masses decreases the speed of light. Okay? The vicinity of mass is just low. So, if nothing else happens, this decrease is equally distributed, equally shifted to the wavelength and the frequency. That's the steady case. And every atom would follow this rule. And, well, I come back to the consequences of this, but now, without knowing it, by the way, I think it was, how should I say, it was bad luck that he got his collaborator Brown's, because the 1957 paper is the really interesting one, not this mix-up of theories, Brown's, Dicke, which is known, I don't know why, maybe. I mean, Dicke was also a great experimenter, and he published it afterwards, but I mean, the real big idea is 1957, it's not Brown's, Dicke. And yeah, you know these funny coincidences. I think it's such a tragedy that these people didn't have an internet. What's happening here? Oh, sorry, I did this in a slow way. So they couldn't know about. But if you look at the paper, I mean, the bold idea, it's 1 plus 2 gm over r. The c squared is missing here anyway. It's 1 plus 2 gm over r c squared. And Dicke says, about the one, he says, does it have its origin in the remainder of matter in the universe? And is this little term involving the Schwarzschild radius on the right-hand side, is this little term related to the gravitational force of the sun? So all this would make wonderful sense if all this sum is 1, is the sum over all masses in the universe done in this manner would be just something like an index of refraction that changes the speed of light. And and you find the very same formula in Denis Sciama's thesis in 1953. I think these are wonderful coincidences, and And people were just not aware of each other. That's a tragedy. So to be a little bit more technical, but to give you a quick idea how Newton's law will arise from that, you have c squared. This formula, c naught squared, would be like a formula at the beginning of the universe, and then you divide by the masses. These are normalized to mass of the universe and the radius of the universe anyway, that cancels out. And by just applying I should hurry up a little bit, just applying the gradient, you get out Newton's law with that nice gravitational constant, which you can debate about the factor of 4, but it's essentially the same as Denis Sciama. So let's go ahead. The second big idea is, Dicke said, we need a different cosmology. Matter could be at rest. Let that sink in. Matter is at rest and just light spreads. Okay? And so, by following up this, oh sorry, I was looking at my slide, I didn't show you that. Matter is on the average fixed in position, and that's his idea. Yeah? An explanation of the cosmological redshift. Matter is at rest, matter does not move, but light spreads. And to get this point across, just imagine, if the presence of masses decreases the speed of light, and if you have light spreading, of course your horizon is increasing, so you have more masses visible in the evolution of the universe. The more masses necessarily decrease the speed of light. There is no way out. You know, it's a necessary consequence if you assume that matter is, in principle, is at rest and light is spreading, which is the most natural thing light can do. So you have this cosmological decrease in the speed of light. And now it's very easy. I mean, you have the two cases, the right one, very well known, light reflection, and of course the frequency does not change, otherwise you would have a break in your, would be unsteady, the light. So it's trivial optics that in the static case you have the constant frequency, and all the shift of the variation of the speed of light goes into the wavelength on the right hand side. On the other hand, if you have the quasi-static case of an isotropic universe at first order, then the wavelength is a constant, and all the change goes into the frequency. Okay? And now in the middle you have the atoms sitting around distributing the change equally to the frequency and the wavelength. And of course, if their personal wavelength is shortening, they perceive the constant wavelength that propagates through the universe as a redshifted wavelength. That's the explanation of the cosmic redshift from first principles. I skipped this test of the gravitation. You can look, anyway, you have to look at this more closely anyway if you want to understand it. Go a little bit deeper, but these are just the 4 tests of general relativity. These are the spatial dependencies, but let's get to a moment to the temporal dependencies, which are interesting for cosmology. And you see that you need to have that consistent framework of everything is changing. So you can postulate that absolute time, which is not directly observable. You have the speed of light, the speed of light. Holy, no, there is a minus. I missed the minus. The minus, it's decreasing the wavelength, and the frequencies are decreasing. The time step is increasing, and so on. Of course, I don't go into too much detail here. But the idea is, of course, as I said before, we have this situation where the universe expands, all elementary particles or wavelengths are shrinking, so you have this relative redshift. And there is another bold thing, I think you remember, Dirac's hypothesis. And essentially, the second hypothesis says that the number of particles in the universe is proportional to the square of the radius, or the square of the time passed. And that's what comes out from that variable speed of light. Cosmology, because if you consider the time step I mean, we measure time with frequencies. If the frequency is going to decrease, our time scale, our local time step needs to increase. So our perceived time has a dependency of t to the 0.75. And if you square that, you arrive at the number of particles t to 1.5, which comes out from the expansion of the universe. I know this is a little bit technical, but I mean, even I would spend another 5 minutes, it would be hard to understand, I admit, if you see it for the first time. So if I convinced it that this is interesting, go and watch more closely to this frame of variable scales. And well, yeah, just Einstein, it's also an agreement, because what Dirac says, the mass of the proton is irrelevant. It's something, it's a message of nature we have to take seriously. And Einstein agrees here, that's what I want to say. He's also, probably if he had known about it, if he had noticed it, he would have been a fan of Dirac's hypothesis. Okay, you can take this a little bit further, what I call one particle Big Bang. If you go back to the universe, so you would have indeed a kind of, well, it's not a Big Bang anymore, because the universe back then would have the size of an elementary particle and then expand, and at the same time the universe back then would be filled with elementary particles. So they have the nice coincidence. So you would have also an explanation of that nuclear density back in time fills the universe. You know? Yeah, this is a kind of summary in between. Just these great thinkers, Dicke, Mach, Einstein, Sciama, Schrödinger, Dirac, they had all ideas independently which have so much in common and they were not aware of. They're even getting into a petty little argument, Dirac and Dicke, very sad. But yeah, what I'm saying here is I would call that big flash cosmology. As I said, matter is at rest, but well, light necessarily spreads and widens our horizon. There is no way that we can keep that light from spreading, so we see every day, we see another portion of the universe. C is determined by the mass distribution in the universe. G is a function of that mass distribution. It's flat by definition. This is another very nice aspect. You don't need all of this stuff and inflation and discrepancies. If you calculate the gravitational constant, I think this is the true solution to this puzzle. The expansion rate decreases with cosmological time. Matter, as I said, universe densely packed with particles. Light starts to spread everywhere. Yeah, at the very beginning we have that infinite velocity also. That's interesting. And it resolves a little bit, I think, the absurdity of time beginning at a certain point, because you have different time scales and you have that infinite velocity at the very beginning at this big splash. So I think also for people doubting that direction, it's okay. Now comes a slide with, I will skip over because I think, yeah, speculations, but even too far for this kind of conference maybe. As I said, it resolves the horizon problem, the flatness problem, and well, I added also this because if you think that the gravitational constant has to be bigger in the past, it's a very natural explanation for a large-scale structure. Why do we have this clumpy universe? Well, because at the beginning of the universe, the gravitational force was much stronger. So we had this early period where all these structures could possibly form. Another thing, thanks to Martin, angular size test of the expansion of the universe. I should do, I admit that, more carefully and technically, but you know, I mean, if you start from the picture, you just look out there in the universe, matter remains at rest. You don't have these contradictions of the galaxy size. It would be very natural, I think, to expect that what is observed. And well, again, going fast over the technical details, there are indeed two versions of variable speed of light. One more conservative, if you want, by Krog and Puthoff and another guy. And they use the exponential, but the problem is they cannot predict the gravitational constant. And our theory, or what I'm more favorable of, unfortunately, I have to admit, we have a problem with the perihelion. The perihelion does not come out right. So if anybody has an idea how to fix that, appreciate it. I don't know. And I also tried a solar system test with gravimetric data. Without much success, the data is inconclusive. And there is also, unfortunately, another serious problem. Doesn't add up with supernova data. It's a huge discrepancy. I couldn't believe it. And I even took into account what Gareth mentioned about the time passing with a different rate. I took that into, at least I thought I did. Maybe I messed it up, but it's a mess. Right now, it's a mess. It does just contradict the data. So we have this situation, and well, I mean, I would argue that we still win, but you know, I mean, if you talk about falsification, you can also say it's falsified. And this is the other version. Would be in agreement with conventional cosmology. Even if you don't believe all what I'm telling you, just consider variable speed of light as a version of conventional physics, and it's, I think, even more insightful. Problems. I already mentioned the problems. There are some nice idea to rephrase the Dirac's hypothesis, giving a little bit more insight about, maybe how to extend it. And we are currently discussing the goals and problems. All of the things I mentioned, I have made a video about. You find that in my variable speed of light playlist, the Hubble redshift, gravity, Big Bang, Big Flash, Dirac's numbers. Also, there is a problem with gravitational waves, forgive me, but that's really a sideline. And here's one period publication. You find not everything, but most of the stuff is here in Annales de Physique. And I have another paper on the archive with my collaborator Jan. And of course, there's my book outlining all this in detail, Einstein's Lost Key. I think we are still underestimating Einstein's variable speed of light approach. Maybe his first idea was the best one. And well, my general point of view is don't get involved in partial problems, but always take flight to where there is a free view over the whole single great problem, even if that view is not yet clear. Thank you very much. Okay.
Excellent. Thank you so much, Alexander. And so if we're going to have questions, let's have folks line up here. Off to the right, so if you can come around the other side and kind of come behind Alexander.
While they're getting started, remember guys, if you haven't signed up to present your 60-second theory, there's a box over on the table at the back of the room. Please put your name in that box.
Can you go to the slide showing Demysticon paper?
Okay. So you are just
I wanted to ask a technical question about
Let me go to Demysticon paper, the Explanatory. It's too many slides. Here we are.
Yes. So actually, interesting. I actually worked in the Sciama building, which is actually named in honor of Demysticon.
Okay, that's really great.
Yeah.
Would you make me understand the question?
What I wanted to ask is, so why you've got this sum, which I suppose can be considered at large distance an integral.
Yes, yeah.
What I don't really understand, if you have a sort of constant density universe, like on large scale, there could be approximation. Then for each shell of some thickness dr and radius r, the mass will be proportional to r squared.
Yes.
And so if you divide that by r, you still have a power of 1 power of r. And if you, so what I'm saying is the interval will diverge.
No.
No, you have to, I mean,
Or is there
I believe in
some
the horizon. There is a horizon.
Right, so this interval is only taken up to the horizon.
Yes. Yeah, good point that you're making. I forgot to stress it yet, but you go until the horizon. And that's why you have all these effects, because the mass is increasing, you're taking into account more mass.
So because the horizon grows with time?
Yes. Yeah.
Ah, okay, so that is why c squared will rise with time.
Will go down with time. There's a lot of dependencies here. G itself will go down.
Oh, I see. So one, okay.
You need to look at the entire picture, even if the masses, because masses are basically inverse acceleration. Accelerations have the unit of meters per second squared, so both units are affected. So it's really a mess if you look at the units. You have to do that consistently. It's not easy. But in that case, as a whole, it will decrease.
Okay. So one other thing I want to mention regarding the evolution of G, of the capital G, would that have any unusual effects on the evolution of the Sun? Because the Sun's been around for 5 billion years, and in the past G was higher?
Yes, you're raising a valid concern. So you need to have, Dirac also already proposed that change of the gravitational constant.
Yeah.
And honestly, we don't have evidence for a change. And there are a lot of people claiming that we have evidence against.
Yes.
Starting from Big Bang nucleosynthesis over heliocosmology,
yes,
over the data from the Viking of Mars, and so on and so forth. My personal take is that most of this evidence is too fancy and too indirect. What I would look for is hard evidence, Earth expansion. You need Earth expansion. And we are more or less, I think, just at the edge of possibly detecting that. It would be something like 0.1 millimeters per year.
But wouldn't the Earth's orbit around the Sun also expand?
Yeah, the Sun would also expand.
No, but the Earth's orbit around the Sun would also expand.
Yes, I mean, you have to take into account. It's really complicated because there is a gravitational effect of this orbit increase, but at the same time, your wavelength also decreases. So we have an apparent increase of the distance if you're measuring this with your variable lasers, you know?
Oh, okay. No, the reason why
sorry, for the sake of the camera, do you think that you could actually stand over here? I'm so sorry.
Yes, okay. The reason I was asking is because there's some constraints on the ratio of the number of hours in each day and the number of, there's a constraint on the number of days per year in the past, about 220 million years back. So I was wondering how this would affect.
Yeah, I mean, I forgot to mention before, there is Edward Teller in 1948 who claimed that there's a G to the 7th power dependence.
Yeah, I wrote a paper along those lines. It's actually about 5.6.
Well, I don't know. Honestly, it's for me, it's a little bit indirect. And certainly, what he didn't take into, I mean, most of these people make the error that they are isolated, considering a change of the gravitational constant without changing anything else. That you have to necessarily have to change anything else too.
I'm talking to the microphone, and Andrew, come if you could stand over here. I think this is
Okay.
Here,
So we have a real debate here.
Okay.
Should I go to the slide with boxing?
No, that's just what I was wanted to ask about the impact on the heliocosmology and the age of the Sun and the relation to radioactive dates and meteorites.
I mean, people would claim, or some people would claim that it's ruled out a change of that order. Well, I'm still unconvinced of that. So, but at the same time, there are lots of problems. I mean, the most concerning for me is perihelion and the redshift distance relation. We need to fix that. If not, no. I don't know.
Sure.
Hi, for those of you who haven't met me, I'm Robin. Thank you very much for a very interesting talk. So, I've read most of your books, I think, and listened with interest to this talk. And I have to say I agree with 99% of what you're proposing. My only issue, and trying to turn to a question, is the origins of variable speed of light. So, referring to your slide in the middle of the presentation where you say variable speed of light in 3 dimensions is equivalent to 4-dimensional space-time curvature. Absolutely. The main difference is that 4-dimensional space-time curvature explains why, for those of us living in 3 dimensions, we perceive matter as causing light to slow down. So the three-dimensional view is a very good descriptive picture of what happens, but it's not explanatory. So, I mean, in our everyday life, we see variable speed of light in lenses as light passes through glass. The photons interact with the electric field around the crystal lattice in glass, and that physically slows down the photons, which is why we get lensing and there's a physical explanation as to why light is going slower through glass or water or whatever.
Yes.
We know on a universal scale that matter causes light to be lensed. I personally myself look at gravitational lensing out in the cosmos, and it certainly works. But that's with the knowledge that it is the 4-dimensional curvature of space that's causing that light to take a longer path and therefore being lensed. So if you purely look at variable speed of light in a 3-dimensional manner, how do you actually explain the cause of that light going slower in the presence of mass?
Okay. I see the point. Yeah, there are a couple of things that come to my mind. First, astronomers doing gravitational lensing has usually less problems and say, okay, that's lensing, that's a decrease of the speed of light. Regarding what actually causes this decrease of speed of light, that's to be done. That's, if you want the microscopic explanation, you would have to model a particle as a wave, as a soliton or whatever, then trying to find solutions. How does that change the environment? How does that in turn has influence on the local speed of light? That's missing, but that would be, I mean, I'm already ambitious here. I think that would be indeed a theory of quantum gravity that deserves the name. You know, it's not a small.
It sounds to me like for this to work in a 3-dimensional world, you've got to believe in something like an ether, which, I mean, some people do believe in an ether. Do you need to throw away the 4-dimensional view in order to work with the variable speed of light theory? I mean,
I wanted to come to this. Yes. By the way, the ether, I think it's a very relevant concept, and Einstein in later years wasn't against the ether. So I have done something also in this direction. However, yes, I would throw away the 4 dimensions. I think it's one of the biggest failures of theoretical physics, and I had a video out there how Minkowski, why Minkowski was a disaster for theoretical physics. And I think this mindless gluing together space and time into something 4-dimensional is the root of serious problems here. Because if you are aware of your senses, there's no reason whatsoever to combine these entities which have a totally different phenomenology, space and time, into something. Oh, it's 4-dimensional, and we define the speed of light at the gluing. No. That's wrong. So I would totally try to get rid of that 4 dimensions. And if you ask the deeper question behind that, the question would arise: why are the 3 dimensions so special, and what mathematical structure can we observe that possibly could reflect our reality in the universe? And that's another book I'm not talking about. That's mathematical reality. It deals with quaternions. But you know, I'm aware of the problem. I may speculate in other directions.
I agree with you on all of that, and perhaps afterwards I can explain why I think fourth dimension isn't really time, but that's another story. All I would say is that if you throw away the four-dimensional picture, that did explain the perihelion advance of Mercury, whereas you're saying you're struggling with that. So,
yeah, maybe you have a point.
So in order to stay on time today, we have to cut questions. I'm sorry, Eric. I know everybody's in line. Eric's on the panel tonight.
Alexander's also on the panel.
Alexander's also on the panel. So if you have questions, save them for the question and answer session during the panel. Alexander, thank you so much. That was excellent.
Guys, good.